Good morning, everyone. It is now 10:01, so we'll go ahead and get started. Welcome to our webinar on regulator performance and selection. We're so glad to have you here today. With a world that's changing around us, we're being very intentional about making sure you still have access to training opportunities, even if remote. After today's session, you'll receive the meeting recording so you can reference back or forward along to others on your team if you wish to do so. Before we get started, just want to go over a few housekeeping items. Throughout the meeting, you will be muted to keep the audio quality clear. However, we do want to encourage questions throughout. So if you have a question, please utilize the chat feature and we'll cover those questions when we reach a good stopping point. To access the chat feature, if you hover over your screen, down at the bottom of the screen, you should see a little button that says chat. So just click that and please feel free to use that at any time throughout. With that, we can go ahead and get started. I'd like to introduce our presenter. John Kestner is Swagelok's Field Engineering Supervisor for the Americas. As an 11-year Swagelok veteran, John started his career with Swagelok as a technical service engineer. He's also held roles as a field engineer and a product manager for General Industrial Valves. From 2015 to 2020, he was responsible for increasing regulator sales by assessing competitive positions and creating development and commercialization plans for those product lines. But more recently, he's taken on the role of field engineering supervisor, where he is tasked with leading a team of regional field engineers across the northern portions of the U.S. as well as Canada. He holds a BS in mechanical engineering from Tufts University, and he is currently pursuing an MBA from Cleveland State University. So with that, I'm going to hand it over to John.
Yeah, thanks, Ashton. Appreciate the introduction. As mentioned, I've spent about, I'd say, 8 of my 11 years here at Swagelok focused in some way on pressure regulators. So it's a topic that I really enjoy and something that I think is really interesting in terms of the different types of fluid system components that we all encounter every day, right? So currently I am in the field engineering role. And that's a team that really can be a good resource for not only the internal Swagelok team, but also all of you. So I encourage you, if you do have, regulator questions or, troubleshooting that you need to get done, don't hesitate to engage the local team and particularly the field engineers. The team is really well equipped to be able to tackle some of those things on a system by system basis as well. So with that, I want to talk about a little bit of the agenda today, and we're really going to cover 2 major topics. We're going to spend most of our time talking about regulator selection. So I've been using throughout my time with regulators about 7-step process to select regulators for a particular application. So we're going to spend most of our time talking about those 7 steps, but I do want to start with a little bit of regulator theory and how these particular pieces of equipment actually operate. That will inform a lot of the choices that we make during the selection portion of the talk. So I'll echo what Ashton said. If you do have questions, fire them into the chat. We've got some pretty good stopping points throughout the presentation, and certainly we'll be excited to answer any questions that you may have. So when we think about the types of regulators or regulators in general, the first thing to consider is, what are we actually asking these units to do? And there's 2 major types of pressure regulators that you see in industry, and that's pressure reducing and back pressure. So pressure reducing are far and away the most common type of pressure regulator. If you hear anybody mention regulator or pressure control valve, most often they're talking about a pressure reducing regulator. And it does just that, right? It takes pressure from a high pressure gas source. So in this case, in the cartoon, it's, you know, gas bottles, but it really could be any high pressure gas source. Reduces that pressure so that it's usable and safe for the process. We want to make sure that we're not going to damage any of the downstream equipment or put the operators in a situation that's not safe for them to operate what's happening in the process. And we also need to make sure that we're giving the process the amount of pressure and flow that it needs. We'll talk more about that a little bit later. Now, on the other side of the process, there's back pressure regulators. And now back pressure regulators actually work in a similar but slightly different way, in that they're all governed by kind of the same inner workings, but back pressure regulators control the upstream pressure. So where pressure reducing regulators are most interested in what's happening downstream, so they're controlling the outlet pressure, back pressure regulators control what's behind them, right? They control the upstream pressure. A lot of times used on process where you may want to limit the maximum pressure in a much more controlled way than something like a pressure relief valve could do, right? You know, a lot of pressure relief valves are designed to drop pressure all at once so that you keep the system safe, right? And you really mitigate any of that risk. Whereas a back pressure regulator will help to control that in a very even way. And so those are most often used kind of on the downstream side of the process to control upstream pressure. Most of our conversation today is going to be around pressure reducing regulators, because those are by and large the most common type of regulator. But a lot of the concepts, they can be applied just the same to back pressure regulators. So if there are questions on back pressure regulators, don't hesitate to ask. I'll be happy to answer. So when we think about pressure regulators, you know, this is a cutaway of a pretty typical spring-loaded, direct-acting pressure regulator. These are, you know, by and far and away the most common type, right? This is a Swagelok KPR series. Obviously, I use Swagelok for all of my examples, but a lot of these concepts can be applied to most any regulator that you may encounter out in the field. And when we think about regulators, there's a lot of components, but we really only care about 3 elements. And those 3 elements work together to do the job of a pressure regulator, which is essentially to divide the system into high pressure and low pressure, right? So within a pressure regulator, there's 2 zones, the high pressure zone and the low pressure zone. And those are divided, or the pressure drop happens at the poppet and seat interface. So there's, in most every regulator, you're going to have some sort of a valve which will interact with a seat, and we call that the control element. So the combination of those 2 is the control element, because it controls the pressure drop, right? So that's really where the work is done in a pressure regulator, is right here at that control element. So as the poppet moves away from or closer to the seat, you'll get varying levels of pressure drop depending on what your system flow demand is. So the control element is a very important piece of regulator performance and behavior. You'll hear me talk a lot about it today. Now, next, we as users, right, of regulators, we need some way to tell that regulator what we'd like it to do. And we do that through the loading element. Most commonly, this is a spring, although we will talk about other loading types, namely dome-loaded regulators, a bit later in the talk today. Most often, it's going to be a spring, which can be compressed or relaxed based on how the user turns this handle, right? So you turn it clockwise, you're going to compress that spring, anti-clockwise, allow that spring to relax. And that loading element is really telling the regulator what it should be doing, what should the outlet pressure be on the low pressure side of the regulator. Now, these 2 elements, the control element and the loading element, they need some way to talk, right? And they need some way to react to what's happening in the system. And that's where the sensing element comes in. So the sensing element's job is to monitor the low pressure side and take an input from the loading element and then tell the poppet where it should be positioned so that we get the right outlet pressure at whatever flow rate the system is demanding. So these three elements, the control element, the loading element, and the sensing mechanism, all work together within a balance of forces. So that's all regulators are trying to do. They're constantly trying to balance all of the forces within that unit so that you get the output that you want. And there's four main forces that we're concerned with. One is the loading force. So we talked a little bit about that, right? That's as the user turns the handle, they're either going to compress or allow that spring to relax. And so that's going to create your loading force, right? So as you compress a spring, depending on the spring rate, you'll get some sort of force out of that. So that generally acts in a downward direction. Now there is an inlet spring force. We'll talk a little bit more about this later during selection, but most pressure reducing regulators have a spring that sits just underneath the poppet to help keep that poppet shut if there's little or no inlet pressure. And that spring does impart a force. It's pretty small, but we need to consider it as part of the equation. That generally acts in an upward direction. Now the outlet pressure force. So this is what we care about, right? This is why we're using a regulator in the first place, is that we want some pressure on the outlet side. Now that pressure acts on the sensing mechanism, the area of that element, and creates a force, right? Pressure times area gives you a force, and that generally acts in the upward direction. And now finally, while a smaller area, the inlet pressure is generally high. So the inlet pressure force is also something we need to consider. And that is the force, again, pressure times area on the poppet. And that generally, again, acts in an upward direction. Now, following along, it's pretty clear how these all balance out, right? The inlet spring force and both pressure forces, outlet and inlet, work to counteract the loading force. And this happens as the system parameters change, as user inputs change. These forces are constantly changing so that that regulator can stay in balance. So a really great example of this is, as the user changes the position of that handle and we compress the spring, the inlet or the loading force goes up, right? We compress the spring, greater loading force. Now the regulator's out of balance, right? Our F1 has gone up, but nothing else has changed yet, right? So it needs to react. The inlet spring force, that's not really going to change in any effective way. The inlet pressure force, for this example, let's just assume we've got a substantially large amount of volume. That's not going to change very much, which leaves the outlet pressure force. The only thing that can react to rebalance that regulator. So as we turn the handle and create a greater F1, we get a larger outlet pressure force. And this is exactly what happens when you set a regulator. You're compressing the spring, throwing the regulator out of balance, the poppet moves to allow more pressure downstream and ultimately rebalance the regulator. You'll hear me come back to this time and time again throughout this discussion because it is the equation that really underpins all regulator behavior when you're using them in the field. So any questions on the theory or operation before we get into selection? I know that was pretty fast, but I like to set up the selection using the operations. Okay, so when I think about selection, I mentioned before that I like to think about it in 7 steps. Now, not all 7 of these steps are as involved as the others. In fact, steps 2, 3, and 4, your inlet pressure range, pressure control range, and flow requirements are pretty much the most important steps when you're talking about pressure regulators. The others like system compatibility or function or system functionality or the end connections, you got to do those with most every component that you select. they're important for regulators too, but it's not something that's specific to regulators and requires a bit more digging into. So most of the time that we spend today, we'll be talking about the inlet pressure range, pressure control range, and the flow requirements, and what effects those have on regulator selection and ultimately behavior. So the first thing is the function of a regulator. And we just talked a little bit about this, right? The two major breaks in function are pressure reducing versus back pressure. So that's really, do you need to drop pressure or are you limiting pressure? Within those buckets, there are some specialty functions, things like differential pressure. So that's if you want to reference another point in your system and have the set point actually track along with that reference pressure. You can do that with a differential pressure regulator. If you need continuous supply from a depleting source, something like a changeover regulator can be very helpful. Or if you need to introduce heat or actually promote phase change, a vaporizing regulator can be very helpful. So there's always going to be these little nuances within each bucket, but the main choice is pressure reducing versus back pressure. So once we've figured out our function, and a lot of times that's driven by your system, right? What do you need? The next choice really is, what inlet pressure capability should I choose for my regulator? And the recommendation always is match it to the maximum expected supply pressure. And that's going to drive a few different aspects of regulator behavior that are driven by, again, you'll hear me talk about these elements throughout this morning, the control element and specifically the seat material more than anything else. So the inlet pressure range is really focused on the control element. You know, some of the other choices will affect the sensing or the loading elements, but inlet pressure range is really focused on that, that control element, which can affect portions of a regulator's behavior, one of which is lockup. So, if you've used regulators before, you've probably experienced this. You may have heard the term lockup, and lockup is the change in pressure when a system that a regulator's in goes from flowing to non-flowing or non-flowing to flowing. So it's this sharp tail that you get right at about zero flow. So if you imagine a valve being turned off in a system, your outlet pressure will uptick slightly. And what that's related to is the force required to shut off the seat. So you'll hear me say this again a little bit later, but regulators are not shut off devices, although they will shut off. So there's an important distinction there in that the regulator's closing force is limited, right? It's you get the inlet pressure that can force the regulator shut plus the poppet spring. And so when a regulator is shutting off, you can imagine if we start, let me see if I can pick up a pen here. So if we start maybe somewhere down here at about let's say 4 SCFM, things are chugging along quite nicely. We're maybe 14 PSI outlet pressure, but we find that the process or the experiment is done. We need to shut it off. So we close that valve. Our regulator is going to work its way back up this flow curve until it's almost shut off. So you can imagine when there's just over zero flow, that poppet might actually be touching the seat. But in order to fully shut off, you need to have some extra force that deforms that seat and creates a full seal. And that's what lockup is. So this tail of pressure is related to the amount of force you need to shut that regulator off. And so when you think about the types of seats that can be used for varying pressures, generally a soft material like an O-ring or an elastomer can be used at low pressure and consequently has low lockup. A harder seat material like PCTFE or PEEK or hard thermoplastic can handle much higher pressures, but require a lot more force to shut off. So you have higher lockup. So it's not only the lockup pressure that seat material can affect, it's also the ability for that particular material to resist what we call creep. So creep is a very common issue that we see in regulators across the board, right? All different systems, all different types of regulators. And that is the increase in outlet pressure over time when the system's not flowing. So it's effectively a seat leak, right? When you have that system shut off. And what mostly drives seat creep is particulate or damage on the seat itself. So we really see two major culprits of seat creep. One is, usually we see these very early in a regulator's life. Down here in the bottom left side is something like a tubing burr, right? A newly assembled system. Maybe there's a burr that didn't get fully flushed out before the system was put together. That burr, because of the small gap here to create that pressure drop, will almost always get caught in that seat if it makes it there. So you can imagine as that poppet then tries to shut, if there's that metal particle in there, it won't be able to deform the seat around that particle, and you'll get a slow seat leak or creep. Now on the further end of a regulator's lifetime, right? So it's been in the system for a while, it's been working well, but over time maybe has accumulated some debris, right? Through bottle changes or whatever else. Over time, you could see regulators develop a seat leak as these particles reach a kind of critical mass, right? And the seat can no longer deform around those particles. So when a regulator is flowing, this usually isn't a big deal because the balance of forces will compensate for any changes in the seat. But when you shut off a regulator, that's where you can really run into some issues. So if we think about creep in this system that I've got up here, the downstream components are selected or can handle the low 100 PSI, but we have a high pressure system. So we need to make sure that we're not allowing that high pressure to bleed into the low pressure side. So if this regulator displayed creep, then maybe this 100 creeps up to 110 or 150, or if it's really bad, you could get to a situation where the high pressure inlet equals the low pressure outlet, which would be very high pressure at that point, right? 3000 PSI. So there are things that we can do to mitigate the risk of creep outside of seat choices, which we'll talk about next. But one of them is filtration, right? So we can filter any particles upstream of a regulator. It's always a best practice if you can include a filter upstream of the regulator. Our standard with integral filters for the models that we sell that have integral filtration is 25 micron. It seems to cut a good balance of particle filtration and lower flow resistance, right? So you don't want to have something that's so restrictive, it'll catch all the particles, but then your flow performance is impacted. So 25 micron seems to be good. You can also add a relief valve just downstream of the pressure regulator. This is pretty common. I see this everywhere, right? It's a pretty common engineering practice, right? Where you have a stretch of the system that needs to stay at a certain pressure. Very often that's protected by a relief valve. It's a really good practice if you're not already doing it. And then finally, one that I think gets overlooked very often is if you can, just shut off upstream of the regulator. Because again, regulators will shut off, but they are not shut off devices. If you have a situation where there is some creep on a regulator, you don't have the opportunity to get in and really crank down on the handle like you would for a needle valve or anything like that, where you can introduce some extra closing force. You're kind of stuck with what the regulator has. So if you can, shut off upstream. It's not always possible, but if you can, it's a good thing to do. So when we think about the inlet pressure range and matching it to the supply pressure, it does a few things for us, right? A, we need to make sure it covers that supply pressure. And B, making sure that we choose something that's most closely aligned with our system might unlock different seat material choices, right? So I've listed a chart here that shows some of the pressure capabilities of different seat choices. So everything here on the right side are all elastomeric seat choices, right? So you can see they are limited to about 1,000 PSI, but they will give you less lockup, right? Less force to close, and they tend to manage creep better. So those particulates that can build up over time have a tendency to just bounce off the elastomer versus embed themselves. And it's also more pliable in that if you do have something that is embedded in that seat, you have a much better chance of it deforming around and creating a full seal again. So if you do have a regulator where you've got maybe it's a system of 800-900 PSI inlet, and you're thinking, well, should I go with the hard seat and extra pressure capability? If the specs call for it, absolutely. But if you have the choice and lockup and creep are a concern, using an elastomer seat can be really helpful. So something to consider there. Now, sometimes the inlet pressure makes the choice for you. If you've got a few thousand PSI inlet, you have to use a hard seat. Just keep an eye on creep for those models because they can show creep just like any other regulator could. So once we've selected an inlet pressure range, right, we need to move on to the outlet side. So we selected for the high pressure zone. Now we need to select for the low pressure zone. And this really is related to the loading element and the sensing element. And choosing a control pressure that's most closely matched to the supply pressure will give us the best control out of that particular regulator. So the first split is a lot like our seat choice, right? Generally governed by what pressure you're controlling downstream. Diaphragm sensing elements, typically used below about 500 PSI. They've got high sensitivity and they will respond quickly to system changes. Generally, they're thin pieces of metal or elastomeric materials, right? So really flexible. They offer a really good sensitive reaction for the regulator, but they are, because they're thin diaphragms, they are limited on what pressures they can control. Now, pistons give you a much wider pressure control range, but because they also vary in size, so lower pressure pistons will be bigger, higher pressure smaller, they'll give you variable sensitivity, right? Sensitivity is a function of the area of that sensing element. They also will respond slower, which initially sounds like all negative, but in some systems like those with positive displacement pumps that might have some residual pulsation, a piston style regulator will handle that a lot better than a diaphragm style will, and can actually dampen out some of that activity. And of course, they can be used at much higher pressures. So the pressure control range also impacts the loading element. So I talked before that the loading element is what we, the users, get to interact with, right? And that sets the outlet pressure. And so what I want to show is what happens to a regulator as the flow demand from the system increases. So this is called Droop. For anybody who's watched a regulator work and changed the flow demands, you've likely seen this or experienced it or even heard the term Droop. It's one of the most common performance aspects of regulators that folks are concerned with. So what I want everyone to watch is just watch the outlet pressure. It's going to decline as we increase flow, but then also take a look, and I'll run through it a couple times, take a look at the control, the sensing, and the loading elements and how they react to the increase in flow rate. So as we increase the flow rate, we're seeing that the poppet moves away from the seat, right? It wants to maintain the same pressure drop with more flow, which means it needs to move further away. But also that allows the loading spring to relax slightly, right? So as that poppet moves away, that loading spring can then relax, which, if we remember from setting a regulator, that means the F1 is actually going to go down. So different than when we were compressing it by turning the handle, that F1 is going to go down. And just the same as setting a regulator, that F3 will also go down by some proportional amount, right? It's not 1-to-1, of course, but it will go down by some amount. And that's what drives your droop in spring-loaded regulators. So spring-loaded regulators, the droop is a function of your spring rate used in the loading spring. So what that means is that if you have a pressure regulator that's going to be used to set 90 psi outlet, right? And you use a 0 to 250 psi control range, that will show some amount of droop, right? Now, if you use the next lowest control range, let's say it's 0 to 100, that spring will actually show better droop performance because the spring rate is lower. So for every millimeter that spring is allowed to relax, you give up less force. And so your droop performance is actually better the lower the control range is. So this is a bit different than what most folks expect, especially having worked with things like gauges, right? Gauges, you want to be in the middle if you can, or at least the middle third. For regulators, they're quite happy to work all the way up to and including the upper end of their control range. And in fact, you'll get a more accurate and a more consistent pressure out of a lower control range than you would a higher control range. And so I think just instinctually, folks select regulators to pair with their pressure gauges, right? It makes sense. Those two go together quite frequently. But the approaches are a bit different, right? Gauges are most accurate in the middle. Regulators actually are most accurate with a lower control range, even if that means operating at the higher end. I can only speak for Swagelok, but I'm sure many others do the same. We make sure that the performance across the flow capabilities is consistent, even at the very tip top of that control range. So if accuracy and resolution are critically important, always try and match that control range with what you expect to get out of the regulator. Now, if accuracy is very important and there's going to be a wide range of flow rates that you expect to encounter, you could consider going with a dome-loaded pressure regulator. So we talked a lot about how the springs drive a lot of the droop, and they're kind of the culprit of inaccuracy in regulators. So we just get rid of them and go with a dome-loaded regulator, which replaces that spring with a pressurized dome of gas. And the flow curves that you see down here are actually the same regulator, so the same lower works, just different loading mechanisms. So this is a spring-loaded regulator, and this is a dome-loaded regulator. So you can see the droop performance flattens out a lot when you get rid of that spring. Now, it does introduce a bit more complexity, added costs, and you do need to design your system to handle a dome-loaded regulator, but it can be a really good option for those systems where the accuracy is critically important. So For pressure control range, we want to match it to the maximum control pressure as close as you can, right? That'll give you the opportunity to not only potentially use a diaphragm versus a piston, but it will give you better accuracy and lower droop. And if droop is a critical concern, you can always go with a dome-loaded regulator. So before we move on to the flow requirements, any questions on the inlet or the outlet pressure control range? Okay. So flow requirements. This is one that I get asked about almost every time I talk about regulators is how do I know how much flow I can get through this regulator? Or I have this amount of flow, what regulator should I use? It is a principal concern of selecting a regulator. And what I always say is that bigger is not always better. In fact, it never is with regulators. You want to find the smallest seat that can carry the flow rate you need. That'll give you the best accuracy and most compliant performance across the life of the regulator. So in order to do that, you want to use first and foremost the flow curves, because these are tested data that's displayed what the regulator is actually doing during a test versus calculations, which are very helpful, especially with larger regulators, but you really can't determine droop from calculations. And we'll talk about both those in just a second. So in terms of flow curves, you can learn a lot, right? There's two primary ways that flow curves are used. One is, will this regulator work for my application? And that's one that I want to cover first. Before we get into that, I'll cover a little bit of what info you can get out of a regulator flow curve. First, you'll generally see some sort of indication of what is the pressure control range, right? You don't always just create a flow curve at the max pressure control range. You try to pick a few different points in between, or in this case, you've actually got two separate flow pressure control ranges denoted by color. So you'll see some info there. You should also see a designation of inlet pressure. So your performance will change based on what inlet pressure you have. And that can be denoted by, in this case, we use letters. Sometimes the actual inlet pressure is printed right on the curve, or there's a legend, whatever it is, but there will be some way to know what inlet pressure do I have. Now the chart, what that tells you is outlet pressure versus flow rate. So as my flow rate changes, how is my outlet pressure going to vary? And that's really what we want to know as regulator users, right? We want to know how consistent is my outlet pressure going to be. So for answering the question of will this regulator work for this particular application, flow curves are a great place to start. So if we have what's a pretty vanilla system, 1000 psi in, 175 psi out, a flow rate of 25 SCFM, and a nitrogen medium. So it's pretty straightforward. The first thing we want to do is find the inlet pressure curves that match our system. So in this case, 1000 psi equals an L inlet pressure. So L. So we want to look at these L curves. Next, we want to find the L curve that covers our outlet pressure. And so to do that, we have to start at our flow rate. So we'll start at about 25 SCFM, and start drawing a line upwards, right? We hit our first L curve. That's not nearly enough pressure, so a set point of 100 obviously isn't going to work. Now, next we continue drawing up and up and up until we hit the next L curve, right? So this one, oh, hey, look at this. It's actually above 175. So we know we can get at least 25 SCFM with 1000 PSI in. And in this case, obviously it's set all the way up at 250. We probably don't even need to do that. We can set it a bit lower and still achieve our 175 PSI pressure limit. So what we know is for this system, a pressure regulator with 1000 PSI in and 250 out will cover 175 PSI at 25 SCFM. So that's one way that we use flow curves. The next is, how much pressure change should I expect from this pressure regulator when I put it into my system? So again, same kind of setup. You can see in this curve, we actually printed the inlet pressures on the curve. Again, you'll see it a couple different ways. But the first thing to do, again, is find the right curve. So in this case, we have 507 PSI or 35 bar inlet pressure. So we know we need to use one of these curves. We also have a static set point, so a zero flow set point at 250. So that means that this 507 curve is the one we want. Now, the question is, when we increase our flow from 0 to 150 cubic meters per hour, or about, just under 100 SCFM, what kind of pressure change will I see on the outlet? So the first thing, find my starting point. Next, I want to find my flow rate. In this case, 150 normal cubes per hour, or again, just below 100 SCFM. Then find the point on the outlet pressure axis and determine what the difference is, right? So if we have our 250 PSI set point, we have about 220 after we've reached our target flow rate. That gives us a 30 PSI difference. And that way we can determine if for that particular system that's acceptable or not. And if we have to go to a more accurate pressure regulator or dome loaded or anything like that. And obviously you can also do that in the bar scale. Now, we also can size regulators using calculations. And each manufacturer has different ways of doing that. For Swagelok, when we do calculate a regulator size, we aim to put that regulator in the 1/3 to 1/2 of the way through its flow capacity, right? So right in the middle part of its capacity, from a flow perspective, is where we will calculate. Now, what we don't get when we just do calculations is any way to know what the droop will be. Now, historically, those were the two choices. A few years back, we created a flow curve generator. So essentially, we took that mathematical model and we applied it to varying flow rates. And it was actually a really cool exercise to do with the product engineers for Regulators, our CFD folks, and came together to create this flow curve generator, which is a little bit of a mix of both methods, right? So it is calculated. They're not tested curves, obviously, but you do get a sense of what kind of droop performance you could encounter. And that is for your specific application. It's available on swagelok.com, kind of available to everybody if you want to use it for sizing regulators. You put in what regulator you're interested in, all of your system parameters, and it'll spit out what kind of performance you could expect. You can also, as you see here, you can compare two separate regulators or the same regulator in a few different systems, and you really get some good flexibility there. So it's a great tool to use if you are sizing or trying to determine regulators for a specific system. Any questions on sizing before we get on to SPE and the rest of the selection process? Okay. So at the beginning of this section, I mentioned that bigger is not always better, right? And one of the principal reasons why is the supply pressure effect. So the supply pressure effect is the way a regulator reacts when you have a changing inlet pressure. So up until now, we talked a lot about what happens when the flow demand changes or the operator changes the position of the handle, and how does the outlet pressure change. But very often these regulators are connected to gas cylinders that over time have a tendency to deplete, right? As you're using that gas, that pressure is going to go down. So what we need to understand is, what does that do to the balance of forces? So coming back to how regulators operate, if we think about the four forces, these will be impacted by a change in inlet pressure. Now, F1 and F2, so the two spring forces, we're not changing the loading force at all. We're also not going to change the inlet spring force because that's built into the regulator. So those two are constant. But as your inlet pressure drops, so will F4, because F4, again, is a function of your inlet pressure. So as your F4 decreases, the only thing that can maintain balance is F3. So F3 is actually going to increase slightly in proportion with that F4 decrease. Now, it's not one-to-one, right? That would be really problematic if you had a gas cylinder that starts at a few thousand PSI and drains down to a couple hundred, if you had the same outlet pressure rise. The amount of rise, which is commonly called the supply pressure effect, is related to the ratio of areas on the poppet. So what area the F4 is acting on versus what area your outlet pressure is acting on, F3. So the ratio of these two areas is what gives us the supply pressure effect. So as a quick example, kind of making the math easy, if you had a 1 millimeter square area on the poppet, so that's your seat area, and 100 square millimeter area on the diaphragm or sensing element, you would have a 1% SPE. So what this means is if your inlet pressure decreases by 1,000 PSI, your outlet pressure will increase, but only by 10 PSI. So 1% of 1,000. So let's look at a practical example to talk through it a little bit. So we have a regulator hooked up to a gas bottle that starts at 3,600 PSI, and we've got an initial set point of 50 PSI. So as my upstream pressure is depleted, 3,600 to 2,600, and we know that this particular regulator has a 1% SPE, that means that my outlet pressure actually increases by about 10 PSI. So as that upstream pressure depletes, the outlet pressure will rise by 1% of the inlet's depletion, which in this case is 10 PSI. For some systems, this is fine. It doesn't cause any issues. But where it does, we need to think about ways to mitigate supply pressure effect. And one of them clearly is just maximize the ratio. So use the smallest seat you can with the largest diaphragm that you can, right? Which in many cases for general industrial regulators is just choose the smallest CV that you can that'll carry the flow rate you need. And that will give you the best supply pressure effect performance. Now, where that's not possible, or you need to have, for one reason or the other, a regulator that still doesn't quite meet your SPE needs, the next best way to mitigate is actually using two regulators. So if we think about what happens with the supply pressure effect at each stage, we'll better understand why this is such an effective way to combat the supply pressure effect. So in this case, again, we start at 3,600 PSI, we end at 50 PSI, but we have a middle stage pressure of 500. So that first stage is actually set to 500, which is in turn the inlet for the second stage. So let's watch what happens as we drop pressure. So we go down this time by 2,000 PSI on the inlet pressure, which creates an increase in the outlet pressure of the first regulator. That's what we expect, up to 520 PSI, 1% of 2,000. Now the second regulator only sees this increase. The change it sees is an upward change of 20 PSI. So it reacts in the opposite direction. So it actually goes down, but only by 1% of the 20 PSI. So down by 0.2 PSI, which if you're looking at an analog pressure gauge, you really won't even notice. It's not going to affect your system. It's effectively eliminated the supply pressure effect. So two-stage systems or two-stage regulators are really effective at reducing the supply pressure effect, especially where you need to use a larger seat for the flow capacity. And they come in all different varieties, right? You can make your own two-stage system like you see here with 2 regulators, or Swagelok certainly does, and other manufacturers do too, where you can combine those regulators into one body. So when we think about flow requirements, again, bigger's never better. Use the smallest seat you can by using the flow curves to determine what regulator is most appropriate. And flow curves are the first choice, of course, and calculations are kind of a second after that. Now, if you can use something like the flow curve generator that we've got, it kind of mixes both, right? But using that small seat will minimize SPE, and you might not even have to go to a 2-stage system. What questions do you have on flow requirements?
John, we had a question just a minute ago. How is
Yep.
the CV calculated? Do we have customized CV values for different customer requirements?
Yeah, so good question. For most pressure regulators, and this is true for all Swagelok regulators, the CV that's posted in the literature is a full open CV. As you can imagine, regulators are constantly changing their CV as the poppet moves closer to and further away from the seat. And so the most consistent position to measure a CV is in the fully open position. That also has the kind of knock-on effect of giving a very good indication of what the fail open flow rate would be for a pressure regulator, which can be really important when sizing things like relief valves or orifices or things like that, right? So a pressure regulator, especially spring loaded, the CV value is determined at its fully open position. And that's why we really don't recommend using CVs to size regulators, because you will be sizing a regulator to operate at its fully open position, which is not a great place to use a regulator, different than the control range, right? You can operate at the high end of the control range, but the poppet really likes to be in that middle section of opening or its flow requirements. So we always default to the flow curves rather than the CV, even though the CV can be really useful for sizing, relief valves and things like that downstream.
Okay, it looks like we have another one here. What is the need of a back pressure regulator when similar operation is performed by a relief valve?
Yep. Yeah, it's a great question. It's something that comes up a lot. The main difference is control. So for those systems where you want to have fine control of your upstream pressure, a back pressure regulator is going to do a much better job than even a proportional relief valve, right? So, things like a safety valve, which slam open, obviously you don't want that happening all the time, every day, all day. But even a proportional relief valve, which opens and closes with pressure, the sensing area on a relief valve is much smaller than a back pressure regulator, which has the whole diaphragm or piston to sense that upstream pressure. So the resolution and accuracy you get from a back pressure regulator is much higher than a relief valve, although the functions are very similar, right? A back pressure regulator can also be used in line, whereas relief valves really aren't. And a good example of that is something like downstream of online process analyzer that, maybe it's used on a liquid line where you want to make sure the pressure is high enough to avoid the bubble point. You typically will put a back pressure regulator at the end of the line so that it maintains that upstream pressure at a high enough level, right? So it provides that control by opening and closing so that you don't run into any sort of issues there. So yeah, great question, and something that definitely comes up a lot, but it boils down to accuracy and resolution more than anything else. What else? Okay, yeah, good questions. So at this point, we've kind of got through all the hard stuff, right? We know what inlet pressure we're using. We know what outlet pressure control range we're using. We figured out how big of a regulator we need. Now we need to get into some of those more detailed questions, right? Are the materials of construction compatible with the fluid that I'm pushing through this thing, particularly as it pertains to the seat and seal O-rings? It's something you do with all components. With regulators, especially for gas, there is one additional effect that we need to consider, which is Joule-Thomson. So Joule-Thomson is a physical phenomenon. It's not specifically brought on by pressure regulators, but Joule-Thomson is the drop in temperature as the gas is allowed to expand or pressure gone down, right? So in a regulator, we're doing just that, right? We're dropping pressure. So we consequently see a temperature drop quite often. And it can be significant, right? You could see, tens of degrees, if not, hundreds sometimes, I guess, in extreme cases. And so it's just something to consider is the system set up to handle that Joule-Thomson effect? For natural gas, you can see about 1 degree C for every 2 bar in pressure drop, which is about 2 degrees F for almost every 30 PSI in pressure drop. So it can be significant. You can compensate for that either by heating the gas or using 2 stages. There's a lot of different methods you can do, and don't ever hesitate to engage the local team, right? If you need assistance there. Now, next is how does the system function? So a lot of this is how do we as users interact with the system? What kind of handles do we have? Do we want a lockout? Where are they mounted? What kind of gauges? How is the system configured? And one of the most important choices is actually venting. So venting is a topic that's really split into 2 choices. That's self-venting versus non-self-venting, and captured vent versus non-captured. And they're 2 independent choices that we'll talk about, not really related to each other. You can have kind of any combination of those as you would want. And it's all based on what are you doing with the regulator, where is it, what kind of fluid is going through it, and what sort of safety regulations do we need to comply with. So for self-venting versus non-self-venting, that has everything to do with where does the extra pressure go. So in a pretty standard, and this is really common configuration out there, is a non-self-venting regulator, which does not give any trapped pressure. Imagine you closed a ball valve just after the regulator, right? And if we turn the handle to relax that spring, the set point's not, or the outlet pressure is not going to change because the gas has nowhere to go or the liquid has nowhere to go. Whereas in a self-venting regulator, we do that same thing, close a ball valve, relax that spring, the outlet pressure is actually going to take over and push this sensing mechanism off this seal. And there's all different seal mechanisms you'll see, but the simplest of which is just a O-ring and then a hole to create your seat that'll push that up, allow that excess pressure to escape. And so that really, self-venting is about, if I'm changing the set points quite often, lab benches are a great example of this, where you're constantly changing set points. A self-vented regulator might be a good choice there. It shouldn't be considered to take the place of a relief valve. The orifice is really small. The sensitivity is not great. So don't have it take the place of a relief valve, but where you're changing set points a lot, totally okay. I think it's a great use for self-venting. Now, captured versus non-captured has everything to do with what happens to that gas or liquid as it escapes the regulator. So for a non-captured regulator, for the Swagelok set, it actually escapes under the handle to avoid kind of blasting an operator if you can, but it does escape to the atmosphere, which if you're outside or in a well-vented area, you've got a non-hazardous media, is probably okay, right? Nitrogen in an outside environment, yeah, it's fine. But nitrogen in a really enclosed space, that can be problematic. And so we want to make sure that we can control where that gas goes should it, either by self-venting or not, right? Maybe there's a problem with the diaphragm that causes a leak. We know where that gas or liquid will go. So in a captured vent model, we will actually include a seal in the stem here and a threaded port, so that you can connect up a male connector or fitting, whatever you have, and actually vent that media somewhere safe, right? Whether it's a drain, a vent, a flare, whatever, you know where it's going. Any questions on venting before we move on?
Yeah, we have one here that says, won't self-vent / captured vent leak system fluid when in the open position? I mean, in operation.
So I think I understand the question. Is a self-vent regulator, is there a chance that when media is flowing, right, you've got a system that's operational, it's flowing, and you've got your high pressure side here, low pressure side here, won't there be media that's continuously venting? And the mechanism here that helps us out is actually the loading spring. So if you imagine, this loading spring is imparting a downward force, right? Just as it does all the time. And that force then is creating a seal between the self-vent seat, which, let me get my laser pointer here, the self-vent seat, which you see here as an O-ring, and the sensing mechanism. So you're actually creating a seal. So as long as everything is in balance, that seal stays shut, and the media can only go through the seat, out the outlet, and that it cannot self-vent. But if we wanted to change the set point, let's say we're doing a new test or a new process, whatever it is, and we want to relax the F1, that then throws the regulator out of balance, right? Now, as a system's flowing, you may not get any self-vent because the system then would just lower the pressure. It's okay because it has somewhere to escape. But if the system is isolated and you lower the F1 by relaxing the handle, then F3 can actually take over, lifts the diaphragm off the seat, and that excess pressure can escape. So if a self-venting regulator is functioning well, you should not have any escaped media in normal operating conditions. Only when there's a sufficient difference between the loading force and the outlet pressure force will you get that pressure relieved. Hopefully that helps. But don't hesitate to let me know if it doesn't. Any other questions on venting? I see these questions come up a lot around venting, and I think that the primary misunderstanding I see in the field is that there seems to be a connection between, well, if I have a captured vent, I must have a self vent, or vice versa, which is not the case. These are two separate choices that you make for two separate reasons, and you can intermix them however you'd like. Any other questions? Okay.
We have another one just real quick. When exactly should a self or captured vent be used?
Yeah, so it's a great question. The primary use of a self-vented regulator, the most effective use, let's say, is when you anticipate changing set points frequently. So imagine a system set up with a non-self-vented regulator, right? So the one we have here on the left, and you constantly are changing from 50 psi to 75 to 60 to 110 to 90, for testing or whatever other purposes, right? And if you had a non-self-vented regulator and the system was isolated, you go to change set points, you would also need to manually relieve any excess pressure. Whereas with a self-vented regulator, those same changes can be made on the fly, and that excess pressure will be relieved, right? So as you change the set point of the regulator, if the loading spring is significantly lower force than the outlet pressure, that pressure has somewhere to go. You don't have to manually vent it downstream somewhere. The regulator will do that for you. So in terms of uses, that's really the best place for a self-vented regulator. Now, when we think about captured vents are all about safety. So if you have a media that is particularly hazardous, or an enclosed space where you don't want to have that nitrogen venting into the air, it would take a heck of a lot, but it could be problematic. That's where you want to use captured vents. So even things like hydrogen, right, that you really wouldn't want venting into the atmosphere. Outside, maybe it's going to float away and it's okay, but inside, certainly, you want the choice or the ability to hook into a threaded connection here, or whatever connection it is, and actually tube that away, whether it's just poking a vent in the roof or going out to a header, again, to a flare, a drain, if it's liquid, whatever. But that's really gives you the ability to direct where that media goes. And actually, one of the most interesting ways I've seen a captured vent being used is almost as like an advanced warning port. So they had connected, we had visited a site where they had connected like a sniffer to that port, so they could tell if there was any issue with the diaphragm. So it was a non-self-venting model, just like you see here, and they wanted to detect the early signs of any sort of diaphragm fatigue. So they could see the small, tiny leakage that might happen as they cycle this regulator quite frequently. So I thought that was kind of cool. But mainly it's about safety and making sure you know where your system fluid is going to go should it make it into the spring cap. Okay, what else? Any other questions?
We've got one here that says, should we recommend customers regulators with or without vent options?
It all depends on the application. The vast majority of regulators used in industry are non-captured, non-self-vent, and they work great, right? For those applications where you are changing set points quite frequently, or you have a safety concern with, should something happen, I don't want this media just venting to atmosphere, that's where you use the captured vent and self-vent, right? So it's not a default. I would hesitate to say that everyone should be using captured vents, because it does complicate your system, right? You need to have somewhere for it to go. There's added expense with installation, and just like everything, obviously you're going to have those trade-offs. So vast majority of regulators are non-self-venting, non-captured vent, but those two options are great for the applications that can use them. Hopefully that helps. Okay. Any other questions? Those are some good ones. Okay. So finally, we look at things you would consider for most any component, right? What are my end connections? What kind of porting do I have? How am I going to mount this thing? The type of connections. Mounting can be particularly important with regulators because you want to be able to see the gauges if they're integral ports, or you want to have easy access to maintainable items, things like that. So always pay attention to how regulators are going to be mounted. Most all regulators being spring loaded, they don't really care about orientation. You may get some effects of gravity if you mount something totally upside down, but by and large, the forces are all going to stay the same. The loading force and the pressure forces are much greater than you would get just by force of gravity of, pulling a component down if it were mounted in an odd way. So mostly it's about access more than anything else. So moving through all these 7 steps, I've been using this kind of cheat sheet for longer than I can remember around, what do you need? What's required to select a regulator? What's kind of nice to have or what's helpful? And then finally, what are those kind of fringe items that just continue thinking about, but you don't need them in every instance or even most instances, really. And so the required stuff is inlet pressure, outlet pressure, flow, and your fluid type. What is it? Is it a gas? Is it a liquid? Is it hazardous? Is it flammable? What kind of things are we looking for? So feel free, I'm happy to send this out to the local team, and, they can share this sheet with you. I'm happy to do that. I think as more folks have this, the better regulators we'll see being used out there in industry. So I'm a happy guy. So in review, to wrap up, and I'll stick around for as long as you guys have questions. I'm happy to hang out and talk regulators as long as you let me. There's two types of pressure regulators: pressure reducing and back pressure. Those are the two main functions, right? The control, loading, and sensing elements, they drive regulator performance. So changes in those elements are going to affect how that regulator behaves. You want to choose your inlet and your control ranges to be as close to your parameters as you can. It's going to give you the best performance. If you can, size regulators using flow curves. Calculations are great. They won't give you any indication of droop, but you can use tools like the flow curve generator to kind of meld those two approaches together. And then finally, self-venting and captured vents. Those are based on the application and what kind of safety concerns do you have on site or for that particular environment. And with that, follow along these steps, and it's you'll get to a regulator that's going to perform really well in 99.5% of applications. So, like I said, I'll hang out. I'm happy to answer any questions, any other questions that anybody might have.
Looks like we have one that says, with vent regulators, should we keep a tab on internal wetted components, spring, etc., to be changed at certain intervals?
Yeah, so it's a good question, right? And one that's particularly interesting for captured vent regulators. So if you have a captured self-vent especially, right, regulator, you could, over periods of time, all of these components are going to be exposed to whatever that fluid is. And so over time, you may want to keep an eye on things like the spring and all that. Now, that being said, we take care to make sure that the materials at construction, at least in our regulators, are pretty suitable for any of those medias that you might get going through there. But it's a really good piece to put in if you're developing a preventative maintenance or an inspection or testing plan. If you have those self-vent or captured vent regulators, is to add those components, right? The not traditionally wetted components to that plan. So springs are a big one. If you have a pretty corrosive media, certainly talk to folks about what spring material might work best, but just add them to the inspection plan. And then in terms of regulators in general, how often, I get that question a lot, how often should we be going in and inspecting parts, doing tests, doing teardowns or maintenance? And the first answer is, whatever the local regulations require. So here in the States, we don't have too much prescriptive regulation as far as pressure control components. Places like the UK and Europe, they're a little bit more controlled as far as how often they need to either maintain or replace. It's, I think, 5 years in the UK that you have to either maintain and test or replace the unit. Generally, what I say is that a yearly test is usually fine for most, inert, pretty standard regulator applications. Go in and you can do a seat test, right? So you just test, make sure you're not getting creep. Shell test, you kind of pressurize everything to the highest control range and inlet pressure. And if everything works out, then your regulator's in good shape. Now, every few years, that 3 to 5 year, you want to think about getting that thing open and inspecting the parts, making sure the seat doesn't have a collection of the debris that we saw in those pictures before. And if it does, clean it right off. Most of the times that's gonna solve the issue. But if not, you can go ahead and replace it with a maintenance kit. But yeah, that's like for most systems, every couple of years is good. But regulators are things that do require periodic maintenance, more so than some others, like, a needle valve or ball valve, things like that. So yeah, really good question.
We have two more here. First, is it best practice to use an isolation valve upstream of a pressure reducing regulator or vice versa?
Yeah, so that's a good one. And it relates back to our discussion on creep, right? So if you can, isolate upstream of a pressure regulator. And that does a couple things for you. One, it allows the regulator to be kind of freed from pressure isolation. So you will have, if you isolate here, vent down the system, you'll have zero pressure upstream, zero pressure downstream. The regulator's happy, right? Now, what it does is, something to consider is that regulator then doesn't have any other forces balancing against your set point or your loading force. So the regulator will actually sit in an open position, which is actually good because you don't want that regulator taking a set on the seat if you can help it, if it's closed for a long period of time. But you will get a slight overshoot when you start the system up. We actually test for this in our production testing. So all regulators go through production testing, and part of that is an overshoot test. Essentially, that regulator seat needs to catch up before it can start controlling pressure. Generally, it's well below 10% of the control range. So, on a 0 to 100 PSI regulator, you might see 3 or 4 pounds of overshoot, and then it quickly gets back under control. So upstream, if you can, that's going to give you the best creep performance. But if you need to, and the system's set up so you have to shut down downstream, that's totally fine. The regulator will handle it. You just want to take the precautions of adding filters and relief valves and everything like that. Yeah, good question.
And then the other one is, I've always been told when adjusting regulators to always increase pressure to set point. Is that because of the spring?
Yeah, so it's actually, it's a good question. I'm trying to see if I have a decent slide for it. Not really. Probably the best one is our flow requirement slide. So the question, as I understand it, and let me know if I'm off base, is the best practice for setting a regulator to set from lower pressure to higher pressure, or the other way around, right? Higher pressure to lower pressure. And you've got it exactly right in that the best practice is always set with increasing pressure. And the reason for that is actually, it's related to the spring, but it's actually a phenomenon called hysteresis. So you see this in all kinds of mechanical stuff, right? And regulators are no different. And what you actually see is if you set from high to low, so let's say you've got a pressure regulator that you're trying to set to 100 PSI, right? Let's make it easy here. We're trying to set it to, let's say 450-ish, right? So we're right here. And we go all the way up. We say, oh no, we made it to 500. I need to back off my regulator a bit. And so you start to allow that spring to relax. You will eventually hit 400, but because of the internal frictions in the regulator, so all those O-rings and the sensing element, the poppet, things like that, you'll actually see that over time, you'll go from 400 down to maybe 395 or 390 as that regulator settles in. Whereas if you go from low to high, you don't get any of that settling out, and you stay in a pretty consistent pressure. So it is always a best practice, if you can, set from low to high pressures due to that hysteresis, which again is not something we specifically covered today, but is a consideration for those types of situations.
Okay, we have a couple more questions here. First, can you explain on the working of dome-loaded regulators with feedback option? Also on the dome to outlet pressure ratio.
Yeah, so let me find, I don't have a good slide that talks about feedback, but I'll try and talk you through it. And what I would say is if you do have a system with a wide flow range, really tight accuracy requirements, talk with the local team and they can get you connected with the right folks and the right pieces of equipment that'll be able to deliver that. So while I don't have a good slide to show you visually, let me talk through it. So a dome-loaded regulator, as I mentioned, swaps a spring for a pressurized dome of gas. Same exact concept. The loading force is then created by that pressure. So pressure times area, this case on the top of the sensing element, creates a downward acting force. Now, in most dome-loaded pressure regulator setups, you've got a pilot regulator. And actually, I've got a good picture of one later on in the slide deck right here, where here's the pilot regulator. This is actually this is a 4-inch pressure regulator, some of the biggest ones that we make, but it's a good example, right? So you feed the dome pressure through this pilot, which you control just like any other spring-loaded regulator. That then sends the pressure to the dome, pressurizes the dome to create your set point, and then any of the excess, and this is, manufacturers have different methods for controlling that dome pressure. At Swagelok, we use this, what we call a dynamic control loop. So basically it's got a tuned orifice on the end of this and controls a very low flow rate through the dome. And so what you end up with is a pressure creating your F1. Now, one thing to remember, and I'm going to skip back to our balance of forces equation, is that we know that we need the F1 to balance not just F3, but also F2 and F4. So very often we describe dome-loaded regulators as one-to-one, right? Whatever you put in the dome, that's what you're getting out the outlet side. When in reality, it's, as most things in reality, it's a little bit messier than that, in that you actually have to have a little bit higher pressure in the dome to get a specific outlet pressure, because you have to balance also against F2 and F4. So your F1, maybe your pressure in the dome is 110 psi, but your outlet is 100. We still call those one-to-one because it's the same sensing element, so that areas above and below are one-to-one. But in reality, it's actually like 1.05 to 1 or something like that, depending on the model. So it's not exactly one-to-one. So good question there. Now, when we think about external feedback and how that plays into pressure regulators, there's a ton to unpack there, and I wouldn't want to do it go into too much detail without a lot of the visuals that we do have. So I would encourage you to contact the local folks, and we can definitely get you set up. But what external feedback does is, instead of sensing the pressure right here, so our F3 is created by the pressure within the regulator. What we can actually do is take a point in the system, right next to what we care about, right? Whether it's a piece of equipment or a process or whatever, and we can create a line, a sensing line, let's just say it's down here, and tube that back to the regulator. And then what we do is we create a little sensing chamber that's isolated from the rest of the regulator and only taking pressure from the system where we care about it. And that gives the regulator the ability to kind of see what's happening in the system versus only reacting to what's happening in the regulator. It gives you really good control, and it's an awesome option for those critical applications where accuracy is paramount. So hopefully that helps.
And then we have one more question. For corrosive or sour gas applications, is there an affordable regulator available, spring type, if you don't want to buy a feedback type regulator media loaded?
Yeah, so we'll go with this one just so I can show you the guts of this regulator. So the question really is, when we talk about hazardous or corrosive media, right? You know, what are the things that we're concerned about? And what always jumps out to me, what I'm most concerned about is a couple things. A, can the seat take it, right? Because if your seat is shot, then your regulator is not going to have very good control, even when it's flowing, and it certainly won't shut off. So is the seat compatible with that material? And actually, let me see. I think I've got a good cutaway of even a piston style, because that's where it gets more interesting. And so not only the seat, but then also any of the O-rings, especially the dynamic O-rings, right? So things like a balanced poppet O-ring, which we didn't cover today, but it moves against the surface in the regulator, much like a piston style regulator seal would. So if those seals get chemically attacked, they have a tendency to swell, and they can actually get damaged or torn and effectively not perform their function anymore. And so you want to make sure that for those types of chemically aggressive medias, that you have the right seats and seals. You know, a lot of the seats we use are PCTFE or PEEK. They're really, really rugged. When you start getting into the elastomers, that's where you can start to see pricier options and you know, specialty type compounds like CalRes and things like that, which certainly will drive costs up. Now, in terms of overall regulator configuration, the other thing to think about is the diaphragm material, particularly for things like sour gas, where the hardness of that material can play a role in its overall longevity. And when you talk about a diaphragm, you've got to walk this fine line, particularly for metal diaphragms, where you want to maintain the ductility or flexibility to give good cycle life or cycle fatigue life, but you also need to have the strength, right, to stand up to these high pressures and forces that we create. So very often there's various heat treatment methods that we use, and we do have options for even just the standard material, but treated a little bit differently for those sour gas type applications. You know, not terribly expensive. Obviously, anytime you start doing those special things, you will drive costs up. But in terms of needing to have a like media loaded dome driven external feedback type constructions, it's not always required if you're careful about the way that you select materials. So what I would say is I would encourage you to contact your local folks. If needed, I'm always happy to jump on a call and talk through some of that stuff, but we've got field engineers all throughout the Americas. So really wherever you're at, there's gonna be someone who can talk to you about those kinds of concerns more than anything else. Yeah, good question. What else?
We have one here that says, is ASTM G93 level C better than ASTM G93 level E cleaned, or is it vice versa?
No, it is. So you've got it the right way around. ASTM G93 outlines the cleanliness levels for oxygen-enriched systems, and the levels are defined by the amount of hydrocarbons per square foot, I think, and they go from A to E, and A being the most clean, right, and then E being still very clean, but just the least clean in that range. And typically, when you're looking at a most common oxygen delivery systems require ASTM G93 level C, and that's also the cleanliness level that Swagelok requires for any SC11 cleaned product, if you've heard that. So we have the ability for most of our regulators to be cleaned to SC11, which meets all the steps for that process, including, bagging and packaging and things like that, as well as ASTM G93 level C. So that's generally, when we call it level C, that means that we just don't package things in the same way that SC11 would require. And most often that's driven by the size of the regulator. So much bigger process-oriented regulators that you see, they wouldn't get put into a double bag. We would use end caps or other methods which aren't specifically called out in SC11. So that's why you see a difference there. But we do have the capability to clean our entire line to ASTM G93 level C if required. Any other questions? All right. Well, as I mentioned before, don't ever hesitate to reach out to the local folks that you have there, or your local field engineer if you know them. Typically the local folks can get you hooked up with them. Or don't hesitate to send me an email. I'm pretty open as far as answering questions. I'll always try and loop in your local teams as much as I can. And I'm happy to be a resource for everybody. So I appreciate the attention, the good questions today, and thank you very much.
Thank you, John. We really appreciate it. And thank you to all of our attendees today.